All right, continuing with section 7.4, let's talk about radioactivity. Experiments have shown that at any given time, the rate at which a radioactive element decays, as measured by the number of nuclei that change per unit of time, is approximately proportional to the number of radioactive nuclei present. Thus, the decay of a radioactive element is described by the equation dy dt equals negative ky for k greater than 0. Note that it is conventional to use negative k with k greater than 0 to emphasize that y is decreasing. If y0 is the number of radioactive nuclei present at time 0, then the number present at any later time t will be y equals y0 times e to the negative kt for k greater than 0. So one very common measure of a radioactive element is the half-life. The half-life of a radioactive element is the time required for half of the radioactive nuclei present in a sample to decay. And it's an interesting fact that the half-life is a constant that does not depend on the number of radioactive nuclei originally present, but only on the radioactive substance itself. And so I put this little cue in for myself to show you why that is. So switching over to the tablet, we're going to derive a little formula. All right, so to find the half-life, remember that y0 stands for the original amount of substance present, and y is the amount present after time t. So the half-life would be the time at which y is equal to 1/2 of y0. And pretty much right away, you see why the original amount does not matter, because in the very next step, I can divide that amount out. And we are left with 1/2 equals e to the power negative kt. So now taking natural log of both sides, we get natural log 1/2 is equal to negative kt. And then remember that property of logarithms that says natural log of 1 over x is equal to negative natural log x. I'm going to use that to write natural log 1/2 as negative natural log 2. All right, and then dividing both sides by negative k, we come up with this formula for the half-life. T is equal to natural log 2 divided by k. And that value of k will be determined by what the particular radioactive substance is. All right, so now I think we are ready for an example. So there's that formula officially. All right, so here's a fun example. A painting attributed to Vermeer, which should contain no more than 96.2% of its original carbon-14, instead contains 99.5%. About how old is the forgery? And they tell me that the half-life of carbon-14 is 5,730 years. So this is referring to what's called carbon-14 dating. It's a method for determining the age of fossils and various other old things, and it could also be used for very old paintings. All right, so let's look at this problem. And by the way, this is technically kind of a pre-calc problem. We're not going to use any calculus in this problem. The calculus is really just to derive the formula that we use. All right, and that formula is y equals y0 times e to the negative kt. All right, and in this case, they gave me the half-life. Since they gave me the half-life, that will allow me to determine the value of k. So using the formula, t equals natural log 2 over k. We have 5,730 is equal to natural log 2 divided by k. And then if you multiply both sides by k and divide both sides by 5730, you get that k is natural log 2 divided by 5,730, which is about 0.00012. All right, so now we have, let me start a new screen here. And we have this formula, y equals y0 times e to the negative 0.00012t. And we're told that this painting has 99.5% of its original carbon-14. And the question is, how old is the forgery? So we want to find the value of t when y is equal to 0.995 y0. So this is going to feel a little bit like that derivation we did a few minutes ago. All right, so once again, the original amount of carbon-14 doesn't matter because you can divide that right out. And we're left with 0.995 equals e to the negative 0.00012t. And now if we take the natural log of both sides, we get natural log 0.995 is equal to negative 0.00012t. Dividing both sides of this equation by negative 0.00012. We get that t, the age of the forgery, is natural log 0.995 divided by negative 0.00012, which is about 42 years. All right. So this thing is definitely not from the 1600s. It's only about 42 years old. Definitely a forgery. All right, I got one more application to show you. And that is, whoops, Newton's law of cooling. All right, so as an example, hot soup left in a tin cup cools to the temperature of the surrounding air. A hot silver bar immersed in a large tub of water cools to the temperature of the surrounding water. In situations like these, the rate at which an object's temperature is changing at any given time is roughly proportional to the difference between its temperature and the temperature of the surrounding medium. This observation is called Newton's law of cooling, although it does apply to heating as well. All right, so here's the formula. I will spare you the details, although it's very similar to the other things that we've been looking at. If H is the temperature of the object at time t, and H sub s is the constant surrounding temperature, then H minus H sub s is equal to H sub 0 minus H sub s times e to the negative kt. And actually, this is really just a special case of the decay formula, because the initial value of that temperature difference would be this H0 minus HS. And then that temperature difference at any time t would be this. So this really is just a special case of y equals y0 times e to the kt. Okay. All right, so here's an example, and then we'll be done with this section. A pan of warm water which is 46 degrees Celsius, was put in a refrigerator. 10 minutes later, the water's temperature was 39 degrees Celsius. And 10 minutes after that, it was 33 degrees Celsius. We're going to use Newton's law of cooling to estimate how cold the refrigerator was. All right, so let me switch over to the tablet. All right, here we go. So we're using this formula, H minus H sub S is equal to H0 minus H sub S times e to the negative KT. All right, so what are we given in this problem, and what do we want to find? We want to find H sub S, which is the temperature of the surrounding medium. That's the temperature inside the refrigerator. And we are given that H sub 0 is 46. We're given that H is 39 when T equals 10. And we're given that H is 33 when T equals 20. Right? All right, so here we go. Filling in these numbers, starting with 39 when T equals 10, we have 39 minus H sub S equals 46 minus H sub S times e to the negative 10k, right? And then H equals 33 when T equals 20 gives us 33 minus H sub S equals 46 minus H sub S times e to the negative 20k. All right, so now basically we just have to do some fancy algebra and solve this system of equations for H sub S. So there might be a different way to do this, but the way that occurred to me is to take this first equation and rewrite it as 39 minus H sub S over, let's make that really look like a 9, 46 minus H sub S is equal to e to the negative 10k. And then take the second equation and rewrite it the same way, 33 minus H sub S over 46 minus H sub S is equal to e to the negative 20k. All right, so somehow I have to relate these two equations to each other. And the way that occurred to me to do that is to notice that e to the negative 20k is actually the square of e to the negative 10k. All right, so now if I take this expression right here and substitute that here, that will give me an equation that I can solve for H sub S. So that equation is going to look like this. 33 minus H sub S over 46 minus H sub S equals the square of 39. Why am I having so much trouble with nines today? Minus H sub S over 46 minus H sub S squared. All right, so let's see, cross multiplying that equation. Of course, you can think of this right-hand side as 39 minus H sub S squared over 46 minus H sub S squared. So if you think of it that way, and then you cross multiply, you know what, I have a better idea. Let's multiply both sides of this equation by 46 minus H sub S squared. I think that'll save me a step. Okay, so on the right-hand side, this and this are just going to cancel, because remember, this is squared. And then one of these will cancel this, and that'll leave me 33 minus h sub s times 46 minus h sub s is equal to 39 minus h sub s squared. All right, so that is a quadratic equation in the variable h sub s. All right, so multiplying all that stuff together, we get 33 times 46, which is 1,518, minus 79 times h sub s plus h sub s squared. And then the square of 39 minus h sub s squared, that's going to be h sub s squared minus 78 h sub s plus 1,521. Okay, so actually this is not a quadratic equation. This turns out to be a linear equation because I can subtract h sub s squared on both sides and get rid of those. And now if I add 79 h sub s to both sides, that'll give me h sub s over here. Subtract 1521 from both sides, and on the left side you get -3. Isn't that nice? So the temperature of this refrigerator, which I guess is actually a freezer, was -3 degrees Celsius. I am a very good speller, and I always have trouble with the word refrigerator. And I think it's because the word fridge is spelled with a D and the word refrigerator is not, which I don't understand. -3 degrees Celsius. All right, and that is going to do it for section 7.4. We'll see you next time.